Okay, thank you very much for the introduction. Today I'm glad to be here to make such a presentation. And this is Yuxuan. I'm going to talk about this paper, Understanding and Detecting Overlay-Based Android Malware at Market Scale, which is mainly a joint work of Zhenghua, Qi, Crystal, Tianyin, and so forth. Okay, let's first look at what the overlay is and what the application of overlay are on Android system. In the screen, I will present four typical things that will illustrate the common usage of overlays. The first is such an overlay which can show system information. An user can interact with them for the detailed data such as CPU and memories utilization, and the temperature of the CPU or the upload and download rate of the current network. The second one is an overlay which is used for voice or video call on top of the screen in a small area. And third is such an overlay which is used for lock screen view. The last is a pop-up message window which can be easily seen in Android system. And such an pop-up message window is also implemented by an overlay. Okay, let's define an overlay more abstractly or more conceptually. An overlay is actually a view in Android system, and an app can create one or more overlays at the same time. Overlays can abstract the contents of the view which is under it. This is because an overlay view is always shown on top of the screen, or we can say an overlay view is always shown on top of other application windows. Here, one thing I want to remember here is that all the overlays we are talking about in this paper are system window overlays. Also, we divided those overlays into 5 common forms. They are the float overlay, which can be a small area float atop the screen at arbitrary location. The cover overlay, which can be a 4-screen rectangle, which completely cover the host view, and the hollow-out overlay, which can be a hollow-out rectangle that can partially cover the host view. The single-point overlay, which can be rather difficult to be noticed, as well as the off-screen overlay, which cannot be noticed by the users. For example, the overlay which is used for voice call is a kind of float overlay. Here, different from the iOS, overlays in Android system can be created across apps rather than within the same app. This greatly facilitates a user's interaction with multiple apps, but also bring some dangers at the same time. Here comes to the issue of, according to the specific form of overlay, there are corresponding attacks leveraged, which are leveraged by them. For example, the float overlay can be used to do some malicious redressing attack, and the cover overlay which can use to do some GUI hijacking attacks, which is based on transparent overlays. And the holdout overlay can be used to misleading users over the meaning of their interaction by manipulating the overlay which cover the host view. The single point as well as the off-screen overlay can capture sensitive input or the UI event. To this end, how can we detect malicious overlays among those complicated things? Are there any characteristics that those different forms of overlay have? So we did an emulation of application experiment to find out the truth. First, we find out all the features that are related to the overlay. Those overlays are including the categories of the appearance, for example, the X, Y, width and the height of the overlay, etc. and the categories of priority, functionality, and flags, which can determine an overlay's capability. There are two static features which can amplify the capability of the overlays. And among those features, there are 4 novel features which are designed for the emulation of the application experiment specially. And we marked in the red rectangle on the screen. Here, one thing I want to emphasize is that most features are listed here are dynamic features which only exist when an app is executed on the user's devices. Next, let me introduce where our dataset come from. Our dataset is all come from the T market. T market is Tencent market, and which has identified and labeled over 2.4 million malicious apps and over 6 million benign apps since 2015. And we used a part of sampled APK from this big database, as well as a modified AOSP system where we added some log codes for the overlay feature extraction. Sorry. This entire work were completed using several commodity servers. And during the emulation, we explore each app by Monkey UI exerciser. Monkey is a kind of tool which can generate UI event stream at both application and system levels. And when Monkey hits an overlay object, it will record the corresponding features which are mentioned before. And then we can extract the overlay features in the overlay logs after the process of the emulation. Actually, here are a lot of more works here. For example, we use binary translation mechanisms to speed up the emulation of the applications. We also design emulators for that purpose. So, but for the limitation of the time, we just ignore those work here. You can refer to our paper for those details. And based on the experiment, I would like to introduce some of the interesting study results. We use Pearson correlation coefficients to describe the relationship between the malice and the features. Also, we draw some figures to illustrate the relationship between those two kind of things. Here in the screen, for feature type, we find that 6 types which are listed in the figures are most frequently used. And 84% of the app which use type system error overlay are malicious. And the PCC between the type system error and the malice of app is as high as 0.69. This is because an type system error overlay is process the highest priority among those types. And for the feature flag, we study all 31 flags in the Android system. We also depicts the statistic of the 30 most frequently used flag in the figures. And we find that 82% of the app which use flag 4 screen are malicious, and the PCC is as high as 0.68. This is because an flag 4 screen overlay can completely cover the screen, including the status bar, so it can deceive mobile user easily. We also plot the heat map of the visual coverage scope for benign and malicious apps overlay. The frame of each figures represent the screen of the common Android smartphones. Again, we notice distinct distribution between the overlays, which coverage scope of malicious and benign apps. Specifically for benign apps overlay, the visual coverage scope tends to locate at the top left corner of the screen. However, for the malicious apps overlay, the visual coverage scope do not have a preferred location at the screen. This indicates that an overlay's x-y coordinate and the gravity are also related to the malice of its affiliated app. And for analysis of other features, please refer to our paper. Next, I'd like to show how we design and implement the overlay checker. First, we use machine learning ways to train our overlay features, which we have extracted from the emulation of the application stage. Second, we embedded the machine learning model into the market and make it become OverlayChecker. Then OverlayChecker takes an app's APK file as input and output its estimated malice of each detected overlay in the app. OverlayChecker checks each app with 3 steps. Step 1, overlay feature extraction. Overlay feature extraction create overlay features for detection. As we mentioned before, it used Monkey to do that. Step 2, overlay classification. Overlay classification evaluates each overlays in app, and the per overlay score are then combined to label the app as malicious or benign with regard to their overlay behavior. And step 3, assisting app review. Assisting app review help App Store vendors to review or release their newly submitted app. Here I want to introduce you some evaluation part of our study. Before we choose random forest model as our final model for detection, we compare the random forest model with other algorithms such as naive Bayes, logistic regression, and SVM altogether. And from the perspective of the efficiency and the performance, we finally choose random forest model. And it is worth mentioning that our proposed for new features improve the accuracy of the detection about 3%. This improvement is not trivial since the precision and the record are already very high. We also use Guinea importance to profile the correlation between the malice of the app and the overlay features. Guinea importance is an inherent criterion of random forest model, and the results are consistent with our measurement finding in the overlay feature behavior study. For example, the type system errors high importance comply with its high correlation with the malice of the app. And our introduced novel features, visual coverage, number of overlay, and is rarely visible, ranked 6, 8, and 11 in their Guinea importance, which also illustrate their contribution to the classification of the applications. For extensibility, we extend our OverlayChecker to Google Play Store. We apply it to 10,000 random sampled applications which are released on Google Play Store. And despite Google's sophisticated security tracking, OverlayChecker still finds 0.2 applications with malicious overlay behavior, and we manually check those suspicious apps and to examine those apps. And we finally find there are indeed some malicious overlay behavior. For example, in the figures on left side of the screen shows all the overlays which an app called Do Antivirus used. And these multiple overlays are all in veiled location and shape. And we find those weird overlays are dangerous enough to be leveraged to do some malicious behavior. So this flag is flagged by our system. We also analyze the robustness of our system. In the learned classification logic of the overlay checker, it may not be difficult for an attacker to pick up features and make it look more benign. But overlay checker is to consider all the overlay features in combination and determine its malice. What's more, overlay checker is data-driven and machine learning based, so it might be possible for an attacker to bypass our detection, but the attacker's difficulty in launching the attack will be greatly increased. Also, we depict a simplified flowchart to demonstrate the branch of overlay check model. And we studied some most recent overlay-based attacks. For example, the cloak and dagger attack, which is a famous attack, which is discovered by Yannick and so forth in the Auckland 17. And we find it can only go through a fixed path, which is highlighted in blue in the figures. And this indicates the robustness of our system. The cloaker and dagger can only go through that fixed path, and it always result in a malicious or the risky classification. Okay. In the end, let's make a conclusion. In this paper, we conduct the first large-scale comparative study of overlay characteristic in benign and malicious apps using static and dynamic analysis. Our result reveals a set of suspicious overlay properties that are strongly correlated with the malice of app, including several novel features. And we also build a market-scale early detection system, OverlayChecker, to address overlay-based attack in the Android ecosystem. It uses a machine learning model that incorporates with static and dynamic application features. And we also deployed its own large-scale Android app store and analyzing 10,000 apps per day on a single commodity server. And we also demonstrate its applicability to the Google Play Store. Finally, we released our dataset on the GitHub. Okay, that's it. Thank you for your attention.